This video is sponsored by Lynn Engineering. Hi, I'm Miles Budimir with Design World Magazine, and we're here with another installment in our ongoing Motion Control Basics series. And this time we're here to talk about stepper motors. One of the most common motors used in motion control applications is the stepper motor. They're used mostly in positioning applications and have the advantage of being able to be very accurately controlled for the most precise positioning applications, down to fractions of a degree, without the use of any feedback devices. They operate in open loop, not closed loop, without the need for tuning parameters as in closed loop servo systems, for instance. Steppers are usually classified by the number of allowable steps they can be commanded to move. So for instance, a 1.8 degree step motor is capable of 200 steps per revolution. It's 1.8 times 200, or 360 degrees, or one full revolution, in full step mode. If operated in half step mode, each step becomes 0.9 degrees, and the motor can then turn 400 steps per revolution. Another mode, called microstepping, subdivides the degrees per step even further, allowing for extremely precise movements. There are several different stepper motor technologies, including permanent magnet motors, variable reluctance, and hybrid types. The principle of operation for stepper motors is fairly straightforward. Traditional variable reluctance stepper motors have a large number of electromagnets arranged around a central gear-shaped piece of iron. When any individual electromagnet is energized, the geared iron tooth closest to that electromagnet will align with it. This makes them slightly offset from the next electromagnet, so when it is turned on and the other switched off, the gear moves slightly to realign. This continues with the energizing and de-energizing of individual electromagnets, creating the individual steps of motion. Hybrid stepper motors are more expensive than permanent magnet stepper motors, but provide better performance with respect to step resolution, torque, and speed. Hybrid steppers combine the best features of both the permanent magnet and variable reluctance type stepper motors. The rotor is multi-tooth like the variable reluctance motor and contains an axially magnetized concentric magnet around its shaft. The teeth on the rotor provide a path to help guide the magnetic flux to preferred locations in the air gap. This further increases the detent, holding, and dynamic torque characteristics of the motor when compared with both the variable reluctance and permanent magnet motor. Stepper motors are relatively inexpensive and can be run open loop, requiring no feedback devices. Also, because the speed is proportional to the frequency of the input pulses, a wide range of speeds is possible. However, while stepper motors are capable of producing high torque at low speeds, they generally are well suited for lower power applications, not for applications requiring lots of torque to move heavier loads. They're best for applications requiring the control of rotation angle, speed, and position. A few drawbacks are that not properly controlling the motor can produce undesired resonance in the system. Also, stepper motors are generally not easy to operate at extremely high speeds, and as the motor speed increases, the torque decreases. A stepper motor's low-speed torque varies directly with the current. How quickly the torque falls off at higher speeds depends on a number of factors, such as the winding inductance and drive circuitry, including the drive voltage. Steppers are generally sized according to torque curves, which are typically specified by the manufacturer.